So I love that. All right. So hi everyone. Welcome. If this is your first time seeing me, nice to meet you, I guess. So a couple of disclaimers before we go ahead and get started. Just remember, we're not directly affiliated with the course. So I mean, I've like me giving the review session, I've had several semesters of experience. But if I happen to say something, maybe logistically, for example, that might conflict with something that Dr. Falzone said, then please get that cleared up with him. Okay. Remember, he's the one who makes the rules of the class, not us. FYI, meetings being recorded. We also encourage you to have your camera on. You know, it's a lot better if I'm like talking to like actual faces instead of just like people or like black screens. So again, not required, but if I see your facial cues, maybe I'll realize that people aren't getting something. And then please keep your questions like to me limited for now. I will pause at certain points to ask for questions, but generally, unless something is like glaringly very confusing, or if I happen to like make a typo or something, then that's okay to ask a question. But otherwise, again, please keep your messages in the chat. Okay, so below I have listed the topics that are going to be covering generally for exam one. This isn't, I guess, too entirely exhaustive or specific, but this is these are the types of things that you should be practicing as you are going into your exam. Okay. For time, I am not going to be going over absolutely everything. I think you guys have already seen enough of MO theory. I will be doing the whole acid-base MO stuff, but I know I want to spend some more time on the stuff that he kind of did last week or this past week and maybe kind of rushed over, leaving people rather lost. So I will start off with a bit of a review of valence bond theory, then I'm going to jump straight into acids and bases, and we'll talk about you know, like the different trends and also how to find your HOMO, LUMO, and all that stuff from there. Then we'll do constitutional isomer stereochem, and lastly, conformational analysis. All right, so let's go ahead and get started. So this is a bit of an overview of the geometry of carbon to begin with. So remember, we can see carbons mainly in this class in three different ways. Either having an sp3 geometry, which is tetrahedral and 109.5 degrees in terms of the bond angle. We can see carbon being sp2, being trigonal planar and having 120 degree bond angle. And then linear, which is sp, and it has a 180 degree bond angle. Okay, so these orbitals cannot really freely, or like, sp3 can freely rotate, but sp2 and sp cannot necessarily or cannot freely rotate because of the fact that these pi bonds are made by the alignment of certain orbitals. Okay, so for tetrahedral carbon, you know, you could freely rotate that. If you have a model kit, which you all should hopefully have one by now, you can experience the fact that you can actually freely rotate those bonds. Okay, your model kit actually goes and then models how each atom or how these structures behave in real life. But some very important things to note: double bonds, please never ever freely rotate them. Okay, and in fact, when you're looking at double bonds, notice that that one pi bond that you have is made up by the alignment of those two p orbitals that I have drawn there. Okay, so the p orbitals that I drew are in the plane of the screen, while as a result, the other two remaining substituents are going to be in the plane that's perpendicular to the screen. Okay, this is very, very, very important. For atoms that are sp2, it's important to note that all atoms bound to sp2 atoms are in the same plane. Or another phrase is coplanar. Okay, and then that extends to double bonds generally as well. Okay, so if I happen to have a structure that maybe looks like this, right? So let me draw out the hydrogens here. So what we're saying by this is the fact that because these atoms are both sp2 and they both consist of, or both of them make up the double bond, what that means for us is the fact that the carbon that's directly bound to that double bond this hydrogen, this carbon, and this hydrogen, all four of those must be in the same plane. So all highlighted in red must be in the same plane. Since the double bond cannot rotate, okay, but then as you start getting along to your other atoms, you'll experience that these bonds right here, they can experience rerotation. Okay, so I'll highlight this in green, but I'll say that this green one right here, because it's bound to an sp3 atom, it has free rotation and is not necessarily in the same plane as the reds. Cool. Usually if we were in person, I would hold out a model kit and show how they all have to be in the same plane, but online's a little different. I can't really show you guys with the model kit, so I encourage you guys to actually build a double bond model on your own, okay? So if you build that double bond model on your own, then you'll realize that there's no way that you can rotate those four atoms that are actually bound to that double bond. Hence, they all have to be coplanar, okay? And this could be extended to things like sp3 as well, sorry, it could be extended to sp as well, the sense that these atoms right here, right, they technically have to lie on the same plane because that sp carbon, or that sp carbon is linear, right? And it's really, really important to note for this that since sp is linear, the bonds should be drawn linear for alkynes. So what I mean by that is you see how I drew up here that alkyne needs to be represented linearly, as you see here. Cool, so this is a good representation. It's gonna pain me to draw this, but helps to see a bad representation. This right here is a bent alkyne. It is totally wrong and will get you points off on your exam. So please get used to understanding the geometry of these atoms and drawing everything properly, right? If something is linear, do not draw it bent, okay? You're gonna be seeing there's many things that I will tell you to not draw. For example, that pentavalent carbons, just name a few, but make sure that you're actually understanding the chemistry behind these carbons and everything else here so that you're not getting things wrong, okay? I'm gonna go ahead and talk a little bit about resonance now. So electron delocalization, okay? So this electron delocalization is possible whenever you have something that we call a pi system, okay? So for example, I know this is something that you guys did in section. We're going to be looking at the acetate ion, okay? So it looks like this. Helps to go ahead and then draw out all of the lone pairs. Now, with something like this, you've probably seen from lots of practice right now that you can go and then draw resonance structures. When you draw these resonance structures, it's important to understand which electrons are in the pi system and can be delocalized. In this case, what we're particularly dealing with is one of the lone pairs from this oxygen, and then the pi electrons from that carbon-oxygen double bond. This is because of a concept called conjugation. And I'd like to define conjugation pretty specifically. That is alternating pi electrons and single bonds. But be careful. Pi electrons, when you think of that, the first thing you're probably going to think of is pi bonds, right? But remember, if you have lone pairs in a pi system, particularly that's when you have an odd number pi system, you can actually have lone pairs being pi electrons as well. So pi electrons can come from pi bonds and from lone pairs. Now, please note that not all lone pairs will participate in a pi system, as you see here. We have 5 lone pairs, but only one of them will actually participate, and you'll see why now. So if I go and I draw my resonance structure, I can actually go and then push my electrons away from the lone pair. So start off from the lone pair, and then form that carbon-oxygen double bond. Doing that will displace this pi bond, and it'll give oxygen a brand new lone pair above. So then, actually, wait, let me not draw that negative charge there yet. So then what you end up getting is this structure where you see that both oxygens still have 2 lone pairs to begin with. But now we've given a third lone pair to this oxygen up here, right? And we've also formed this new pi bond. Okay? So these are the 2 possible resonance structures that we can draw. Now, if I go and I draw that resonance structure, you're going to notice that I will probably not get full points on my exam for this resonance structure that I drew. One thing you always have to keep in mind is formal charge. Okay, and there's a bit of a rule for when you're drawing resonance structures that regards formal charge, and that is that all resonance structures for a certain compound must have the same overall formal charge. Okay, so if I'm drawing one resonance structure that has a -1 formal charge, that means that all resonance structures that I draw need to have a -1 formal charge as well. So as I've drawn that right there, it looks neutral. I have to put my -1 formal charge there somewhere. So helps to kind of go and then count your valence electrons, okay? So to start off, just remember the fact that when you're calculating valence electrons, each bond has 2 electrons. 1 electron corresponds to each atom in that bond. So for example, when I look at this bottom oxygen over here, notice that for this bond would count as 1 electron for oxygen. This bond would count as 1 electron for oxygen. That's just because the other electron would be for carbon. Now we can go and then count and see how many valence electrons we have. So we have, so far, I've counted 2, 3, 4, 5, 6. So this oxygen has 6 valence electrons. How many valence electrons does oxygen have in the periodic table? It has 6. So that means that this oxygen is neutral. Now I'm going to erase everything here, or like this, all these arrows. Now let's go and then look at the other oxygen. The other oxygen, you see, has, again, 1 electron here for oxygen, 2, 3, 4, 5, 6, 7. This one has 7 valence electrons. So here, because I have 7 valence electrons, that oxygen is going to have a negative charge. So please remember that rule. If you have an extra valence electron, you have a negative formal charge. If you have one less valence electron, you have a positive formal charge. So that's how we calculate it. Again, please make sure that you don't forget formal charges when necessary. Okay, might be a very small thing, but at the same time, that's a very easy way to lose points on your exam. Another thing about organic chemistry. You never have a formal charge past plus or minus 1, right? So your possible formal charges are -1, 0, and +1. So don't go giving oxygen a +2 charge, for example, or giving carbon a +2 charge, for example, because you won't be seeing that. Okay, that's only something that you primarily see with ionic species. So that's a generic resonance structure. Let me quickly talk about hybridization. So when you're looking at hybridization, you want to look at the electrons that are going to be permanently bound to each atom, right? The, the electrons that are delocalized are not going to be hybridized. So we're only really looking at the things that are going to be permanently bound. So let's see exactly what is permanently bound here. Make everything the same color. All right, so let's start off by looking at this first oxygen over here. Well, when we're looking at what's common between both structures, you see that we have a lone pair here, a lone pair here, and then the sigma bond over here. So we only have 3 things that are permanently bound, right? That pi bond is not permanent, and that third lone pair that's in the second structure is not permanent, not common between both structures. So when you think of it, you only have 3 things that are 3 orbitals that are hybridized, and that'll be spp. So that means your hybridization of oxygen is going to be sp2. When you're looking at carbon, let me erase some colorful stuff here. So the carbon below that, well, when you're looking at the things that are permanently bound, you notice that this carbon-carbon bond is there in both cases. The carbon-oxygen sigma bond is there in both cases. And then the carbon-oxygen sigma bond over here is common in both cases. Okay. Again, only 3 permanent orbitals, spp. It's going to be sp2 hybridized. Then for that last oxygen, so you see once again that the things that you have in common are going to be lone pair here, lone pair here. I forgot to add an extra lone pair for this. Yeah, so those 2 lone pairs are common. These 2 lone pairs are common. And then the sigma bonds here is also common, right? The pi electrons and that extra lone pair, they're only present in one structure. So even though oxygen looks sp3 in one structure, it's actually going to be sp2, okay? That's just because the lone pair that's delocalized is not going to be hybridized, okay? You could think of it as in maybe one structure looks sp3, the other one looks sp2. If you're choosing between sp3 and sp2, go with sp2. So that third oxygen is going to be sp2 hybridized, right? So little rule, whenever you have things that are in a pi system, right? Conjugation usually occurs whenever you have, when you have a bunch of sp2 atoms in a row, right? So everything you'll be seeing in a conjugated system, for the most part, will be sp2. Now that last carbon that we didn't talk about, this nth carbon over here, well, you have 3 hydrogens here on this carbon. And it doesn't have any pi character associated with it at all. So because you have a total of 4 permanent bonds on that carbon, it's going to be sp3 hybridized. Okay, and then don't worry about the hydrogens. Hydrogens are like just as hybridized. But when we're looking at hybridization, we are looking at every atom that is not hydrogen, right? So here we have found the hybridization of every carbon and oxygen atom, okay? So make sure you're considering this when you do hybridization for conjugated systems. Cool. Yeah, so now I'm gonna go ahead and jump straight into acids and bases if no one has any questions about what I've talked about here so far. All right, so trust me, I've held this review session several times and I've noticed that if I spend too much time on valence bond and MO theory, I don't really have much time to talk about acids and bases. And acids and bases are very, very important in organic chemistry. In fact, every reaction you're going to be seeing from the first reaction you see in this class to the end of Orgo 2, that involves acid-base chemistry, pretty much every single step. Cool. So for acids and bases, we're going to be considering 5 different trends. Or I guess I usually call it 4 different trends, but and then one of them is a subset of one of them. So the 4/5 trends that we're looking at are going to be electronegativity, there's also going to be size, induction, and resonance. And the one subset I am talking about is hybridization. Hybridization, as you know, is a subset of electronegativity. So let's go ahead and take a look at that. So first, the big thing you want to observe with electronegativity is that the more electronegative atom is happier with a negative charge in the conjugate base. Okay, so what that means is that the more electronegative atom will be the fastest to gravitate towards a negative charge. Okay, so the examples that I give usually are ethanol and ethylamine. I like to throw a lot of names around. Don't worry about nomenclature too much. The amount of nomenclature that Falzone tests on exams is pretty minimal. Okay, so yeah, when you're looking at ethanol versus ethylamine, what you first want to do is identify the most acidic proton. Okay, and here it's actually pretty easy to identify the most acidic proton because it's just the proton that is on the most electronegative atom of each respective species. So in this case, the most acidic proton is the one on the oxygen for ethanol and the one on the amine for ethylamine. Okay, so then remember each of these consists of some sort of you can have some sort of a reaction with a base. So here I just have a generic base. And what's going to happen is that the base will come in and attack a proton, sending your electrons over to the electronegative atom, right? So what I'm doing right now is something called deprotonation. In doing that, I end up depositing a lone pair onto oxygen, hence giving me a negative charge on that conjugate base. Do the same thing here as well. Notice that every time I'm doing this, I have my electrons flowing from my electron donor to my electron acceptor, right? So I'll talk about what that means in a little bit when we talk about our HOMOs and LUMOs. Okay, so here are our 2 conjugate bases. So looking at this, you know that oxygen is the more electronegative atom in the periodic table. So because of that, this is going to be the overall most stable conjugate base. If your conjugate base is more stabilized, then that means that your more acidic species is going to be your ethanol. So this is going to be your strongest acid of the two. Cool. So then that's the big trend that you've got to see with electronegativity, just seeing how it's stabilized with the conjugate base. With hybridization, which is a subset of electronegativity, you're going to be depositing the negative charge. Actually, forgot the extra lone pair on this nitrogen. Yeah, with hybridization, a species with greater S character is more electronegative. Okay, so because of that, we can go and then, so because of that, we can go and then see how things would change when we have something that's sp versus sp2 versus sp3, right? Because as we know, sp is more electronegative than sp2, sp2 more electronegative than sp3, and it keeps going. All right, so let's go and check that out. So again, when we go and we react a generic base with our acid starting material, we can go and again have our electrons flow from our electron donor to our electron acceptor. In order to generate our conjugate base, okay, as we see here. Do the exact same thing for an sp2 and then an sp atom. Then sp. And then that gives us our negative charge here in this final product, okay? Note that every time I have my electrons coming from my base, I generate a conjugate acid with that as well. So technically it would be this plus, imagine each of these plus your conjugate acid being H base. Again, I'm just using base as a generic base, but in real life, you would actually be using some sort of a real base. So what do we observe here? So we notice that this carbon is going to be sp hybridized. This one's sp2. This one's sp3. Same exact thing with our products. Cool. And in doing so, we realize that again, that we have the negative charge on the more electronegative species. So because of that, we see that because this is a more stabilized conjugate base, the alkyne, the one of the sp hybridized carbon, is going to be the strongest acid of the three. And as you would expect, this bottom one would be the weakest acid. Cool. So that is electronegativity with the umbrella of hybridization. Now with that, I'm going to go and then start talking about size. So what's the deal with size? Size is going to come into effect whenever you can go and then stabilize the size of, or stabilize the atomic radius. So By that, you're doing some stabilization by decreasing the distance between your nucleus and electron shell. Okay, so when looking at electronegativity versus size, electronegativity only really matters. Let's say this is our periodic table, as you go down a row. So if you're going from left to right, the trend would be electronegativity. And then size matters down a row. Okay, so as you're going, down a column rather. So as you're going down a column, you would want to be looking at size as opposed to electronegativity. So the most common example that we use for this are our halogens. So do hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. Okay, so as always, you want to go and then react it with your base. And let's see how that ends up going. Well, remember that each of your halogens has 7 valence electrons. And as you're going down, remember that the size of your atom increases. So you could think of the fluorine's atomic radius being about maybe relatively this size, chlorine being this size, bromine being this size, and iodine being the largest of all. Let's see how our conjugate base looks like. When we go in an attack, we see that now our atom has 8 valence electrons as opposed to just 7. So remember, you've added an extra valence electron onto your electron shell. That extra electron will account for extra pull on the nucleus. So as a result, the size ends up getting smaller. Look at the same thing with hydrochloric acid, hydrobromic acid, and hydroiodic acid. And we see that now they all end up getting a total of 4 valence electrons. Sorry, 8 valence electrons, not 4. But remember, as we add that extra electron, the nucleus gets smaller. Right? So if you think about that distance between the nucleus and the atomic shell, we're accounting for some sort of energy there. So let's say this is the atom, and then this is our nucleus. Okay, that's not too perfect. Yeah, that's fine. So remember that if our electrons are present in that green shell, and then we have our nucleus being in the middle, there's some sort of energy that accounts for this distance. And the big thing that you're going to be seeing in this class is that greater energy means less stable. And less stable means more reactive. So of these, we see that iodine has the largest radius. So it means that there's going to be a greater amount of energy accounting for that distance between your nucleus and your electron shell. So because of that, iodine is considered to be the most reactive and hence the strongest acid. Likewise, the trend keeps going for the other sizes, and we end up seeing that the weakest acid is your hydrofluoric acid. Okay, so this one is a bit tricky because we're talking about the stabilization of the size of that, of the size of that halogen, right? So even though the fluoride technically has the smallest radius, the the iodine is overcoming the lowest energy barrier out of all of them simply because of the fact that it is so reactive. Okay, so that's why we consider hydroiodic acid to be the strongest out of these four. So now that we've talked about size, we're going to go ahead and look at induction. I'll leave this up for like maybe like 10, 15 more seconds so people can copy things down. All right, so number 3. This one is going to be induction. Now, induction, remember, that involves withdrawing electron density. Towards a specific group via a dipole moment. Okay, so common examples that we can see are maybe things like carbonyls, right? Which you know that oxygen is more electronegative. So it'll have a partial negative, carbon has a partial positive. You're going to be observing some sort of a dipole moment going in that direction of that electronegative atom. Another example that you could probably see is a halogen, for example, fluorine. Fluorine, most electronegative atom in your periodic table, partial negative up here, partial positive down here. You're going to have a dipole moment going in that direction as well, right? So the whole concept of withdrawing electron density is not necessarily by an actual physical resonance structure, right? It could just be via the presence of an atom that maybe just wants to have electron density because it's so electronegative. So let's go and then check out our examples. So I'm going to be showing you guys 2 different examples. One of them is going to be induction via the presence of a group. So rather, I'll say presence versus, or inductive group versus no inductive group. So let's do this compound, actually no group here, versus a group that does have that fluorine there. Cool. So a little bit of a preview into the next, the next trend that we're going to be talking about after this. But this proton right here for that carboxylic acid is pretty mighty acidic due to the fact that it forms a stable resonance structure, which I'll talk about in a little bit. But what we see here is that the base can come in and then deprotonate over here in order to give us this conjugate base. Same idea over here. Cool. So hopefully, now that we're talking about dipoles, I can show you guys the reason why that particular proton is so acidic. Remember, this guy would be partial positive, this guy would be partial negative as a result, right? So remember, if you're partial positive, you want to accept electron density. So when you observe this, you notice that oxygen has a negative charge on itself, right? So in the top example, you don't have an electron withdrawing group to actually stabilize, right? Or you don't have anything to counter that negative charge. However, going back to the whole concept of dipoles that I talked about earlier, if this carbon is partial positive, or like if that fluorine is electronegative, then the atom itself will be partial negative while the carbon is partial positive. Well, remember, we like having opposite charges nearby each other. So what's really nice is the fact that this partial positive can be stabilized by the negative charge that's on the oxygen that you see here. Okay? It's much better to have a positive charge to counter that negative charge as opposed to no positive charge. So because of that, this bottom example will be your strongest acid. Okay, so that's the example of having an inductive group versus no inductive group versus having an inductive group. So the other example of induction that we can see is proximity. So let me start off by using this exact same example. And let's say I were to go and then move the fluorine closer. Cool, so we observe the exact same thing. We have the partial positive and partial negative from that electron withdrawing group. But now our big difference is the fact that we have a partial positive that's closer to that negative charge induced by the oxygen. So because we have this, remember, as I said earlier, it's opposites like being next to each other. Opposites attract. So because of that, we can observe that these guys are much closer than the partial positive that you have above. And because of that, having that positive charge, that opposite charge closer to that negative charge will overall be more stable, making the closer electron withdrawing group more acidic. So this is your strongest acid of the two. Cool. However, of course, having an electron withdrawing group is still better than having no electron withdrawing group. So if we were to rank the relative acidities of the three, your most acidic would be this compound, then this compound, and then finally the one that does not have the group on there at all. So going from most to least acidic based off of induction. Cool. So when in doubt, if you're not entirely sure about how induction works, feel free to draw in those partial charges and see how that stabilization would work. Okay. Now I'm going to go ahead and then talk a little bit about conjugation or resonance, which is our last big trend in acids and bases. Resonance and conjugation are essentially the same thing. And the rule is that longer pi systems are generally more favorable. Cool. So I'll show you some examples of this now. So let's have this. Yeah, let's have this. Okay. So what makes acetone decently acidic? under the presence of a strong base. Well, first you want to go and then consider what your most acidic proton is, which here we actually only have one option for an acidic proton. And that's going to be the protons that are going to be in that position next to that carbonyl. We call this the alpha position. So if we were to deprotonate there, we would end up getting a negative charge on that carbon, right? With a lone pair, of course. So this is a bit interesting because we straight up just went and deprotonated an atom that was not really that acidic. However, there are many different things that are coming into play here. Okay? For starters, you technically have induction because now you have a negative charge next to a partial positive, which is great. Okay. You also have hybridization. But Juan, what do you mean by hybridization? We just deprotonated something that was sp3. Well, yeah, we did just deprotonate something that's sp3. However, the resulting product was sp2. So not only did we go and then basically unhybridize one of those orbitals, but we also put a negative charge on a species that prefers it rather than sp3. So that's favorable. But the big thing here is resonance. Now remember, this thing becoming sp2 is pretty good because now that means that we can actually put those electrons into the pi system and we can get a favorable resonance structure. So we can actually go and then push our electrons over to make a carbon-carbon double bond and then send your electrons up to oxygen. Okay, in doing so, we can get a nice favorable resonance structure. Cool. So fun fact, if you're taking Orgo 2, you'll see this functional group, but I like dropping names in here. This particular functional group is called an enolate. So if you remember, keep that word in the back of your head, you'll see it in Orgo 2. You'll be like, whoa, I remember that from like several months ago. Cool. But yeah, this is just one example of conjugation. Okay, another example of conjugation kind of ties back to the example that I just did for induction. Where I start off with already a 3-atom pi system. However, I can make it into a more stable 3-atom pi system by introducing electronegativity, or like some differences in electronegativity here. Rather, what I'm saying is that the conjugate base over here would be more stable because of the fact that when you draw the two resonance structures, you end up observing that both oxygens end up getting a negative charge, at one point. When you compare this other one, you draw your resonance structures, you'll end up observing, by the way, the gray arrows and the blue arrows that I'm drawing here are two totally different ones, so don't mix them up. Here, I'll remove the gray ones. Notice that the two resonance structures for my starting material are a little less stable than the resonance structures for my product because we have a positive charge on an oxygen, which is not preferred. So overall, these will be much happier than what your starting material is. Cool. So notice that we're overall doing essentially the same reaction here. Of these two that I've drawn, which do you think is going to be the stronger acid? (50-50 chance?
The bottom one.
Why the bottom one?
Because there's the other oxygen that's more electronegative than the carbon.
Absolutely, very good. So yeah, both of these are decent acids, but the more acidic one overall would be the one with the oxygen, right? Because oxygen prefers having a negative charge as opposed to carbon. So these two, not because of resonance necessarily, but actually because of electronegativity, this one is going to be more acidic. All right, cool. So these are our trends in acids and bases. Next thing I'm going to talk about is going to be applying our knowledge of acids and bases into our knowledge of MO theory. Okay, this is something that people tend to struggle with, but it's also tends to be a pretty heavy question on Dr. Falzone's exams. So it goes without saying that you should not ignore this. Cool. So acid-base chemistry with MO theory. Cool. So those of you who went to my learning den on Wednesday are probably familiar with some of these examples by now, but I'll just quickly go over it because I think it's still pretty important. I like to base my starting point around hydrogen. Okay, so here I've drawn a proton, a hydrogen atom, and a hydride. In terms of valence electrons, we have 0 for proton, 1 for hydrogen, and then 2 for our hydride. Okay. So of these three, the only one that can possibly donate electron density is going to be the hydride. So proton is always going to be a LUMO. Hydrogen is actually always going to be LUMO as well. And the hydride will always be a HOMO. So now you're probably asking, all right, what orbital will be the one that's filled when you go and attack? Or what orbital will be the one that donates its electrons? Well, for protons, the orbital is going to accept your electron density is going to be your empty s orbital. On the proton. For LUMO, well, hydrogen, if it's going to be bound to something, it's always going to have a sigma bond to something else. Okay, for hydrogen, your LUMO will be sigma star. And then for hydride, your HOMO will be your non-bonding lone pair on the hydride. Okay, you can also write this as just lone pair on hydride. Okay, so this will always be, so this will always be like how you're going to be seeing these, right? So hydrogen, if you're talking about it with respect to hydrogen, then that'll always end up being that'll always end up being a LUMO, although compounds that contain hydrogen could also be HOMO as well, right? But this one, whenever you see this is a guaranteed LUMO. Whenever you see this is a guaranteed HOMO. Right? If you have a hydrogen, that hydrogen might not necessarily participate in the reaction, but the overall compound could still be a HOMO. So I'm going to go in and draw some examples with this. So I'll start off with my favorite example to use for this, formaldehyde. So here I'm showing formaldehyde reacting with a proton, okay? Here, remember that I have a dipole moment where I have a partial positive on carbon and a partial negative on oxygen, okay? So of these two, oxygen, even though it's partial negative and doesn't really like having a positive charge, it's the one that's going to readily want to go and then donate its electron density. So to show this, at first, I personally like drawing a little dotted line to show the new bond that's forming. And remember, you always want to show your electrons flowing from your electron source to your electron acceptor, right? So drawing it to the dotted line, or if you want, you could just draw it straight to the actual compound. Then you end up with this product here. Again, for this arrow notation, electron source, electron acceptor. So here, what's my HOMO going to be?
The N on oxygen.
Yep, the non-bonding lone pair on oxygen, right? So that's just because the lone pair is going to be what's going to be donated into that proton. And then what's the LUMO going to be?
Empty s orbital.
Empty s orbital, perfect. Cool. Now, bit of a side note for these acid-base reactions. When you're talking about formal charge, again, I'm stressing formal charge because it's very important. Remember that your overall formal charge for your starting material should be the same as the overall formal charge for your product. So here you see that your overall formal charge when you're taking everything into account is +1. Here the overall formal charge is also +1. Okay, so make sure that you guys are keeping that in mind. And again, when I'm saying overall, that's taking into account everything that's in your solution. All right, so I'm going to use formaldehyde once again. And I'm going to use, let's do maybe hydrochloric acid. So a little bit of a hint, this is why knowing some names is important. If something has the word acid in its name, then surprise, it's an acid. So again, we're going to be looking at what can potentially donate electrons here. You might think the chlorine might want to donate electrons, but the issue with chlorine is that it's just way too electronegative. It doesn't want to handle having a positive charge. So because of that, that's for sure not going to be your HOMO. Okay, so instead your HOMO is actually still going to be the same thing. And it's going to be your lone pair on oxygen. So what's going to happen is that we're going to go ahead and attack here. And as a result, we're going to go and then donate our electrons onto chlorine. We're going to break that sigma bond. Okay, so we see our HOMO is going to be exactly the same, the non-bonding on oxygen, but here our LUMO is going to be sigma star. It's sigma star because we broke a sigma bond in our LUMO. Cool. And I'll list these out at the end, but anti-bonding orbitals can only be LUMOs. They cannot be HOMOs. Okay. Another example, I'm now going to be using hydride. Well, in the case of hydride already has a good amount, or it already has 2 valence electrons, has a negative charge. It cannot accept anymore. So now it wants to go and actually donate its electron density. So we see a partial positive and partial negative as always. But now, because we have a negative charge on the hydride, that negatively charged hydride wants to gravitate towards a partial positive carbon. So as a result, you can go and attack and then send our electrons up. And then we end up getting this negatively charged species, right? Again, we're still keeping the formal charges consistent. Also, for this one, I forgot to include the chloride product. So then HOMO and LUMO. So our HOMO, again, we have lone pairs coming from the hydride, so it's going to be the non-bonding on our hydride. And then our LUMO, we're breaking a pi bond. So similar to how we broke a sigma bond earlier, our LUMO is going to be pi star. Cool. So these are the three examples I'm going to show you about this for now before I move on to the next thing. But just as a big takeaway message, when you're thinking of HOMO and LUMO, so when you're thinking of the orbitals that are always going to be HOMOs, you can think of these being your sigma bonds, sigma bondings, your pi bondings, and your non-bonding lone pairs. For the orbitals that are going to be LUMOs, there's actually a bit more. It'll be your sigma anti-bonding, your pi anti-bonding, non-bonding, I don't think I've seen it as a LUMO, so no. But then also your empty s orbital, on your protons, or your empty s orbitals, sorry, empty p orbitals on either boron, aluminum, or carbocations. So big takeaway is that you're never going to see a bonding orbital being a LUMO. You're never going to see an anti-bonding orbital being a HOMO. Okay. Remember, HOMO is constructive interference, whereas LUMO is destructive interference. So whenever you see bonds breaking in your LUMO, that will be your usually an anti-bonding will be your LUMO. Okay. Any questions on this before I move on? I think I'm going to do stereochem first and then constitutional after, time permitting. Okay, so yeah, I just want to do stereochem because that's going to take some time. Okay, so for stereochemistry, essentially what we're dealing with is the spatial arrangement of atoms based on carbon's geometry. Cool. So we know that carbon, when it's sp3, it's tetrahedral. So it adopts this shape. Cool. So yeah, so whenever you're considering things for absolute configuration or whatnot, you got to start with the fact that carbon is tetrahedral when it's sp3. We have a separate set of absolute configuration for sp2, but we're going to talk about that maybe later if we have time, but that's not as complicated as maybe this initially. So the big thing where stereochem comes into play is when we have 4 different substituents on carbon. When an sp3 carbon has 4 different substituents, we have something called either as one of four names. They all mean the same thing, by the way. We have a chiral center or a stereo center or stereogenic center or asymmetric center. Cool. So what I mean by four different substituents is that we have some sort of different groups over here. And all these are absolutely not the same thing. Cool. So yeah, four different names for that chiral center thing. Yes, people couldn't make up their minds. That's fine. Okay, so now let's go ahead and see some examples of this and how we can actually designate the differences between other ones, or between these types of compounds. Okay, so for example, we can have something that looks like this. Okay, so this particular compound has four different groups. So this is considered to be, this carbon is considered to be chiral. Maybe compare that to a group that looks like this. Here we observe that there are two different groups that are exactly the same. So this is not a chiral center. Cool. So now when we go and look at chiral centers, we can actually find something called absolute configuration. For chiral centers, we have two different types of absolute configuration. And that's either R, which means your three highest priority groups are clockwise, or S, where your three highest priority groups are counterclockwise. Okay, so with this, we can go and then see how different molecules might look when, how different molecules might look when you have different orientations. So when I'm talking about priority, we rank priority based off of molecular weight. Cool, and it's a very, very, very specific system for finding this. So I'll walk you guys through some examples and you'll see exactly what we mean by that. So now we want to go in and see how to find absolute configuration. So to find absolute configuration, see if your three highest priority groups are clockwise or counterclockwise, when the fourth priority is in the back, okay, so let's look at this example. So same molecule I drew up here. So when we're looking at this, we want to look particularly at the atoms that are directly bound to that carbon, right? So this carbon here labeled in red is your chiral center. And these are going to be the carbons that are directly, or the atoms that are directly bound. So looking at these, we see that one atom is very clearly very clearly has a higher molecular weight. So that's going to be first priority. So we see that this oxygen up here is going to be our highest molecular weight. So it means that this group, which is called an alcohol, we see that that alcohol is our highest priority. So we will label that as 1. Then for your other ones, well, carbon, they're both the same, or like they technically both have the same molecular weight, but then that hydrogen is going to be your fourth priority. It's going to be in the back. We did a different color because that's not going to be part of our clockwise versus counterclockwise. So when we're defining the priority of these two, what we want to do is actually first look at the carbon and see exactly what these things are bound to. So let me actually go and then redraw these. So again, looking at these atoms right here that are directly bound to that carbon. So I'll call this carbon A and I'll call this carbon B. You'll see that carbon A is going to be bound to a carbon, a hydrogen, and a hydrogen, right? And we're not counting that carbon in the middle. We're just counting everything else past that. Carbon B, on the other hand, is bound to just 3 hydrogens. Cool. So looking at these, we want to go ahead and start looking. We want to actually kind of like put these things head to head. So first, we want to look at carbon versus hydrogen and see which is going to be higher priority. In this case, carbon is your higher priority. So that means that the side with carbon A will be your second priority, and the side with carbon B will be your third priority. So this is second priority, this is third priority. Now we want to go ahead and see what direction we're going in. So we see we have 1, 2, 3. You got a good color here. Yeah, whatever. Yeah, 1, 2, 3. We want to go in this direction. Cool. So we see that that direction is counterclockwise, and we see that our lowest priority is dashed, meaning that it's pointing towards the back, which means that this is going to be S. Cool. So little complicated, could be a bit of a tedious process, but unfortunately it's something that you have to do if you want to pass exam 1 and the rest of this class. So yeah, make sure that you are staying on top of your stereochem. Please employ the help of your model kit when necessary, because some examples do start getting extremely wacky. Okay, let's do another example. So let's say we have this example, okay? A bit simpler because now we have 4 different atoms like bound directly to carbon, so we don't have to do that CACB thing. So looking at this, our highest molecular weight is, or our atom with our highest molecular weight looks to be iodine. So we'll call that 1. Then it's bromine, then oxygen. And then we see that our lowest priority is pointing out at the front. So we're going to want to consider something very important when we look at that. So you see we have 1, 2, 3. We're going in this direction, so it looks like it's going to be S. However, our lowest priority is pointing directly in the front. So it's actually going to be flipped. Meaning that even though it looks like it's going to be S, this is actually going to be R. Cool. And if you actually physically take your model kit, you'll see exactly how much that makes sense. Cool. So now I'm going to plug in my laptop, but then we're going to start talking a little bit about how to relate 2 different molecules. Okay. So when you have 2 different molecules with the same molecular formula, but different spatial arrangement, what you can end up seeing is that there's going to be some sort of a relationship based off of that spatial arrangement. So we have 3 different types of relationships, or 3 main types of relationships that we can see. And these are going to be your enantiomers, your diastereomers, and just identical molecules, right? And here I'll also take this opportunity to define constitutional isomers as well. So relating compounds via stereochem. So first, we're going to have enantiomers. Actually, I'll start off with identical because that's the most obvious one. And trust me, when I say something's obvious, I mean it's obvious, not obvious, but then it's not obvious to you. So identical molecules literally means that the molecules are the same based off of absolute configuration and whatnot. Okay, and for molecules to be identical, you need at least no chiral sensors, meaning molecules can be identical if there is or is not chiral sensors. Okay, so that means that, like, let's say if I have these 2 molecules, let's do this and this. Then here, even though they look like they're mirror images of each other, they do not have any chiral sensors on them whatsoever. So these guys are identical. To do an example with a chiral sensor, let's do this. So the way that two identical molecules with a chiral center would look like, we'll rank these 1, 2, 3. We go in this direction. Looks like it's going to be going clockwise, so that's going to be R. And then over here, you see that you have 1, 2, 3. Looks like that. It looks like it's going to be S. But you have to flip it because your lowest priority is pointing to the front. So it's actually going to be R as well. So this is how identical molecules would look like. For enantiomers, you've heard the definition over and over. These are non-superimposable mirror images. And for this, at least one chiral center is required. So let me take this example right here. And I'll just quickly change stuff because of time. Cool, so these molecules look exactly the same almost, except they're actually flipped, okay? So when you go and then do this, you see 1, 2, 3. In this case is going to be S, and you don't flip anything because of the fact that your lowest priority is pointing out of the back. So this is a key thing you see here. If you have the exact same structure, the exact same constitutional isomer, then if you have R in one structure and then you have S in the other structure, that means it's going to be, that means that they're going to be enantiomers. Okay, so just to show some more cases. So let's say we have compound A and then compound B. If compound A had absolute configuration S, then B would, for an enantiomer, B would be R. If I had SSS, B would be RRR. If I had RSR, then B would be SRS. If I had SSRSRRS, then what would my enantiomer be?
The RRS, RSSR.
Yep. So RRSRSSR. Right. So you can pretty much do this entirely just based off of your chiral centers. Cool. The next one is going to be diastereomers. So whereas identical molecules were mirror images, just not superimposable, diastereomers are absolutely not mirror images at all. Cool. And then there are pretty much two requirements for this. Either at least two chiral centers, or cis and trans possibilities, about a double bond or ring, okay? The big thing is that diastereomers still have to have the same molecular formula. So let's see. So here are two examples so here's an example of a pair of molecules. Now, each of these molecules has two chiral centers. So you have one here, and then you have one here, one here. So when you go in and find your absolute configuration, see that this is first priority, second priority, third priority. You go in this direction, this is going to be R. And then for your other one, again, I don't have time to go in depth as to like how these priorities work, but with practice, you'll get it. For this one, this is going to be 1, 2, 3. So it looks like it's going to be R. However, because of the fact that your lowest priority is implicitly pointing out at you, so it's pointing towards the front, you're going to have to flip it. So it ends up being S. Cool. Likewise, when you go and find your absolute configurations for this next one, both of these will be R. Cool. So the reason why I flipped that S one was, again, if that hydrogen is not drawn out, just remember that it is implied to be coming out. Cool. So RS versus RR, these are not mirror images of each other, so they can be considered diastereomers. So similar to what I did above, I'll do the whole molecule A and B thing. So we can have molecule A being RS, B being RR. If we have maybe molecule A being SSSS, maybe B could be SRSS, for example, right? Just changing one out of those will be good for making an entirely different diastereomer. Maybe we have RSRR. Someone give me an example of a possible diastereomer.
R.
Yep, RRRR, right? Okay, so these are just possibilities. Of course, there are many, many different more possibilities, but I'm not going to draw all of them out because we would be here literally for like the next like 100,000 years. Okay, so that's for chiral centers. You can also have cis and trans about a double bond. Remember, think back to what I said at the very beginning of this review session. If you don't remember, I understand because your brains are probably very fried right now. But remember that double bonds do not have free rotation because of the alignment of those p orbitals, right? So here we have a trans double bond. The absolute configuration for that would be E. Here we have a cis double bond. Absolute configuration for that would be Z. Okay, so these are both non-superimposed, or these are not mirror images of each other at all, because if you look, they just don't actually look like they can be mirror images. There's no way to rotate that trans into a cis. So that's one example. And this other example, I got endless questions about this when I TA for this class over the summer. But when you have your substituents about a ring like this, notice that these are not chiral centers. However, because carbon is, again, tetrahedral, these carbons are sp3, there is no way to rotate this first one into the second one, right? If you don't believe me, build out your cyclohexane on a model kit and try it out, okay? But these are going to be two different diastereomers, right? This is cis, and this is trans. And you can never rotate cis into trans or vice versa. Cool, so that's diastereomers. And then lastly, constitutional isomers. Okay, so constitutional isomers have the same molecular formula. But different overall structure. Okay, so classic example of two possible constitutional isomers could be maybe this structure versus this structure, right? So they do not have the same connectivity at all. They cannot even be enantiomers, diastereomers, and of course not even identical. Notice that they're different connectivities because these guys have a 1-3 relationship, the methyl groups, and the methyl groups over here have a 1-4 relationship. Cool. So again, these are going to be constitutional isomers, and you guys are doing different types of problems on this. So hopefully you know what a constitutional isomer is, okay? And in terms of those types of problems, just make sure there's no real systematic way of solving those types of problems. You kind of just have to go and then do lots and lots of practice. Cool. All right, any questions on stereochem? Before I talk about one last thing about stereochem. All right. And then the last stereochem thing I will quickly talk about is meso compounds. So meso compounds, these are very, very specific types of compounds, and they have specific requirements. So meso compounds are symmetric and optically inactive. But they have a plane of symmetry. That's part of what symmetric is, but yeah, so they have a plane of symmetry. They have at least 2 chiral centers. And they, the 2 chiral centers must be opposing configurations. So as an example, here's 1,3-dimethyl cyclohexane. I'll make both of these wedged. So we want to go and then see if we can possibly go and then identify this as a meso compound. First, we want to check to see if we have a plane of symmetry, which, as you can see here, we absolutely do have a plane of symmetry. So it's right on here. Next, we want to see if we have at least 2 chiral centers, which it appears that we do have at least 2 chiral centers because we have one over here and we have one over here. And then lastly, we want to see if our chiral centers are opposite configurations about the plane, which they are, because when you go in and find your absolute configuration, you end up seeing that this one is R and then this one is S. Okay, so this is an example of a meso compound that's optically inactive. Cool. You're going to see many different types of examples of meso compounds, but this is just one of them. Make sure that you guys work on lots of practice so you can see many different examples of meso compounds. All right. Any questions before I move on to conformational analysis and energy? Cool. So there are many different things that we can do with conformational analysis, particularly when we're dealing with energy. And this is really the other like math heavy quote unquote part of the class. So the first thing I'm going to be talking about is cyclohexane. So cyclohexane, when you draw it on paper, that's how it looks like. That's not really how cyclohexane would look like in real life. So what you have to do is draw cyclohexane as something that we call a chair. So a bit of a roughly drawn chair, but it'll do. So this is how it looks like, okay? Now watch carefully as I draw the substituents on my chair. So we want to alternate between things, between two different positions called axial and equatorial. So what I'm going to do is that I'm going to draw everything that points up first, and I'm going to draw everything that points down. So the point of these chairs is that every single atom has one, or every single carbon has one substituent that points up and another substituent that points down. So let me number this 1, 2, 3, 4, 5, 6. And they alternate in these positions called axial and equatorial. So carbon 1, you see, is axial. So this is up axial. Axial just means pointing straight up. 2 will be up equatorial, meaning kind of pointing off to the side. Carbon 3 will be pointing up axial. Carbon 4 will be pointing up equatorial. Carbon 5 up is axial. Carbon 6 up is equatorial. Okay. So notice that I'm alternating for the same direction between up and axial and equatorial, right? So you see 1, 3, 5 is axial, 2, 4, 6 is equatorial. And then for the substituent that points down, it's going to be the opposite of what you initially had. So if carbon 1 had up axial, then it's going to have down equatorial. So you'll see down equatorial over here, carbon 2 down equatorial here, carbon 3 down equatorial, carbon 4 down axial, sorry, carbon 2 is down axial, not down equatorial, carbon 5 down equatorial, carbon 6 down axial. Cool. So make sure you guys practice drawing chairs. Remember that each chair has each carbon has one thing that points up, one thing that points down, and also one of those is axial, one of those is equatorial. So notice that you alternate between up axial, down equatorial, then down axial, up equatorial, up axial, down equatorial, etc. So I'm going to do some color coding over here, and I'm going to denote everything that is axial in red. And then everything that's equatorial in yellow. All right, so I don't think I missed anyone. All right, beautiful. So that's one chair. And then we can actually go and to represent energy or like different energies of the chair, we can actually do something else, which I'm about to draw right here. Take 2 of drawing a chair. All right, so kind of looks like our little Budweiser logo. So, or Facebook Messenger logo. But now that I said that, you guys won't be able to unsee that. So yeah, now I'm gonna go and then I'm gonna repeat the same pattern that I had earlier, but this time I'm actually gonna start numbering my carbons from over here. Right, so 1 over compared to what we initially started numbering with. So 1, 2, 3, 4, 5, 6. All right, so I'm gonna go and draw in my substituents again. So we have up axial, up equatorial, up axial, up equatorial, up axial, up equatorial. Then for down, we have down equatorial, down axial, down equatorial, down axial, down equatorial, down axial. And then the whole point of this is now that everything that was initially axial will now become equatorial. So notice that all my little red beads will become equatorial, but still point in the same direction. Then now my original equatorials will now be axials. Cool. So this here is what we call a flip. Song reference. Okay, so, oh, I forgot one. Yeah, so notice that everything that was initially axial now went equatorial. But something really, really important to realize as well is that we are not changing the direction of any atom, right? So notice that, for example, carbon 1, I'll label this with a little smiley face for good vibes. Carbon 1 was pointing up, or like the substituent on carbon 1 that was red was pointing up, okay? Now we just flipped it to equatorial, but it's still pointing up. So nothing ever changes direction. We go from up axial to up equatorial, or from up equatorial to up axial. You never go from up axial to down equatorial. That will not happen. Cool. Now I'm quickly going to go ahead and talk about the interactions that can occur. So there is a handy dandy chart on the back of your exam. If you look at your back tests, that lists all these values. Please do not waste time trying to memorize them because you don't have to. If you want to impress your friends and be cool, I guess that's a different story, but I don't know. I wouldn't be that impressed if I was your friend if you just tried reciting numbers to me. Okay, so let's say I have So let's say I have a structure that looks like this, right? Where I go and where I want to go and then I want to calculate exactly what kinds of energy I have. FYI, the methyl Me is from methyl group, so CH3. You'll see that notation quite a bit from here on out. So I personally like going and drawing in all my axial hydrogens, and I want to see exactly what kinds of interactions we have. So first I can note that I have this interaction right here, which is called a 1,3 diaxial interaction. So these in red are 1,3 diaxials, and these are both worth 3.8 kilojoules per mole according to the table. See, I just went and had that whole rant about people memorizing numbers when I've done this too much and I've already memorized it myself. So yeah, these are 3.8 kilojoules per mole. And then over here, we have these these interactions that we call a gauche interaction. And this is also actually worth 3.8 kilojoules per mole. Total coincidence? So now we can go and then calculate the total energy that is responsible for this structure. And we could just do that by adding up all of the possible 1,3 diaxial and gauche interactions that we have. So we have two 1,3 diaxials, then we have our one gauche, and that gives us 11.4 kilojoules per mole. Cool. So that's going to be, so that's going to be the overall energy that accounts for that one structure. Okay. So how do I get gauche interactions? Actually, I'll start off by talking about 1,3 diaxial. So for 1,3 diaxial interactions, the way that you can get those is by basically seeing what axial groups are interacting with what other axial groups on there, right? So you won't have a hydrogen-hydrogen 1,3 diaxial interaction, but you can have a methyl-hydrogen 1,3 diaxial interaction. Just as an example. Now I'm going to go and then flip my chair. So and this methyl group now points up. This methyl group now points down. And then this methyl group now points up. And I'll show you guys how to get the Gaussian interactions after this. So now we can see how much energy we're accounting for here. So we have our axial hydrogens here. And we can go and then draw in our 1,3 diaxial interactions. So in this case, we actually have a total of 4 1,3 diaxial interactions, right? Because that comes from the methyl group and the hydrogens pointing up and the methyl group and the hydrogens pointing down, okay? This case, we don't have a Gaussian interaction anymore because of the fact that both of our methyl groups are axial. Again, I'll show that in a bit. And then this one lone equatorial methyl group, it's not close to any other group. So if it's equatorial, it's not going to account for any energy. So essentially, the energy that we have here is going to be 3.8 times 4. So that gives us a total of 15.2. Yeah. Cool. So now we can actually find the energy difference between the two chair conformations. And that's going to be 15.2 minus 11.4, and that gives you a whopping 3.8. In case you haven't noticed, 3.8 is a very recurring theme for this exam. Cool. So now when we're talking about Gaussian interactions, actually, should I? Yeah, I'll quickly talk about Newman's first and then go back, because my explanation of Gaussian interactions involve Newman projections. So Newman projections, so they look like these. I know Dr. Falzone loves to have his little joke about how this is your Mercedes benzene. It says that every year. So Newman projections look like this. So we can have two different types of pretty much configurations for our Newman projection. What we see here on the left, this is called your staggered conformation. And this one over here is called your eclipsed. So when we're looking at these, essentially what we realize is that our eclipse is actually more of an intermediate. However, overall, what the Newman projection represents is pretty much like a straight on view of a molecule. So let's say we have a molecule that looks like this. Essentially, what we're doing is that we're taking this molecule and we're looking at it from this angle. Cool. So if I happen to call this carbon 1 and this back one carbon 2, then this would be carbon 1 and this would be carbon 2. Okay. Another drawing for that would just be like this, with wedges and dashes. Okay, again, this is carbon 1, this is carbon 2, and we are looking at it straight on. Cool. So with Newman projections, we can actually go and then do some sort of calculations here, and I'll show you the calculations right now. So let's say I have a Newman projection that looks like this. What we can actually do is rotate let's see. So we can actually end up with a structure that looks like this. So I'll show you what I mean by rotate in a little bit. So what I did is that I just went and I rotated the back carbon. So some color coding here. So notice that here I went and I simply rotated what was back here to this position. Okay, so essentially just carbon 2. So we needed to overcome something here called a barrier to rotation. Okay, so essentially we need to overcome some energy in order to actually go ahead and then rotate from one conformation into the other. Now, to do that, we actually had to go and then identify in which direction we're rotating. So we see that we went ahead and we rotated this one in this direction. We rotated this one in this direction. Then we rotated this one in this direction. Okay, so we just went ahead and we rotated 120 degrees clockwise. So in between that, in between these two staggers, we had to have an eclipse in the middle. Again, eclipse tends to be very high energy, meaning very unstable. So eclipse, we only really see that as an intermediate. So we notice that the front stays the same. And then we have our green hydrogen over here. Then we have our yellow methyl group. And then we have our red methyl group. So over here in this eclipse conformation, we go ahead and we actually have to go and calculate how much energy is associated with each of these interactions, right? There's some strain involved with this. So you see we have energy, which actually is 6 kilojoules per mole as from your table in the back. This is 11 kilojoules per mole. And then this is 6 kilojoules per mole. Cool, so just out of curiosity, so for your eclipsed, your hydrogen-hydrogen eclipse interaction is 4 kilojoules per mole. Hydrogen-methyl is 6 kilojoules per mole. And then methyl-methyl is 11 kilojoules per mole. But that's not all. We also have some more energy that we have to consider. So after we add these up, we get that our eclipse is going to be 23 kilojoules per mole. Sorry, I just got this laptop. I want to try and find a way to mute those notifications. So yeah, so eclipse is 23 kilojoules per mole, but we also want to go ahead and then find our initial gauche interactions. And the way we get these initial goals is just by finding the interactions between adjacent methyl groups. We just want to count the number of adjacent methyl groups. And you see that we have a total of 1, 2, and 3. Each of those accounts for 3.8 kilojoules per mole. And when you go and you multiply 3.8 times 3, you get a total of 11.4 kilojoules per mole. Now to find your barrier to rotation, you just have to go in and subtract the eclipsed energy minus the initial gauche. So your barrier equals 23 kilojoules per mole minus 11.4 kilojoules per mole. And that's going to equal to, let's see, 23, 13, 12, 11.6 kilojoules per mole. So you're probably asking yourself, why do we just use the eclipse and the initial gauche, and why don't we use any of the final gauche? So remember that this is just a barrier, right? We need to overcome some sort of an energy barrier to actually go and then rotate. So what we're saying is that if we had some sort of an energy barrier that looked like this, so where this is the initial conformation, this is the final, or the initial staggered rather, this is the final staggered, and then this is the intermediate, and then this is the intermediate eclipsed. That energy is just the gap between your initial staggered and your intermediate eclipsed. Shouldn't use I for both. So initial. Initial staggered, final staggered, and then intermediate eclipsed. Well, I know it's 6 o'clock. I'm just quickly going to talk about the gauche interactions for the chair, and then afterwards I'll be done. But yeah, so then this is just rotation and energy. All right, and then the last thing I'm going to quickly talk about is just our chair. So thinking back to our chair, we can actually, what I'm going to do is that I'm going to just isolate this part of the chair over here. We can actually think of the chair as a chair conformation as putting two Newman projections together. So kind of like this. Okay, so right now I'm only going to really be focused on just like one half of it, but it's both the same. So remember that whenever you have a gauche interaction, your gauche interaction is based off of neighboring groups that you see here. Okay, so notice that this one would be up axial, right? Because that's just this guy up here. This is down axial. This is down equatorial. And then this is up equatorial. So what we notice here, let me actually do this in different colors, is that the three ways to get a gauche interaction is if we have both substituents either being both up on adjacent carbons, we can also have them both pointing down, or we can have them both being equatorial. Okay, and then this has to be on adjacent carbons. So yeah, so for Gaussian share. Again,
Hey Juan,
yeah.
you messed up the arrows for your equatorial on your chart. So it should be down axial with up
Oh,
equatorial.
yeah. Thank you. Down, up. Yeah, so that must be on adjacent carbons. In order to have a Gaussian interaction. All right, cool. So that's it for me. I know I couldn't get through everything, but you guys will be doing lots of practice in your pilot session this week. I also want to remind you guys that I am the Learning Den tutor for this class. And if you want to drop by Learning Den, my link is on the Learning Den website, and my hours are Tuesday 1:30 to 3:30 p.m. Eastern, and Wednesday 7:30 to 9:30 Eastern. Drop by, we'll do lots of practice problems. It'll be fun. And yeah. So,
Yeah.
Yeah.
Yeah, if you guys are feeling a little shaky about this conformational analysis stuff, it's going to be on this week's problem set. So you'll get more practice with it. You can ask your leaders for more help. So don't be too worried about that.
Yeah, so I hope you guys all found this helpful. I know it was a lot of material to cover for a review session, so I tried my best to condense it. But if you have any other questions, please don't hesitate to reach out to your pilot leader or myself if you want. All right, so thanks for joining us. Enjoy the rest of your Sunday, and we will see you all in pilot at some point.
Good luck on your guys' exam.
Are you
Good
guys
luck.
going to be posting the notes in the video from today?
So I think we're only going to be, if for some reason like you couldn't watch part of the lecture, just fill out the poll that I sent out in my email on Friday, and then we'll like hook you up with the recording.
Cool. Thanks.